Welcome, Math 30-1 to Trigonometry, Functions and Graphs, Lesson 6, found on page 543. I'll give you a minute just to cue that up in your own workbooks. You can press pause if you wish. All right, as previously discussed, what a periodic function is something that has a repeated pattern over a regular interval. And it has to be a regular interval, otherwise over the domain, otherwise it would not be periodic. We don't need to test periodic functions to see whether or not they are. We're going to assume that the values that we are given are in fact periodic. The amplitude I talked about before, like we saw the tuning fork, that it showed how high up or down the graph goes away from the median line, the middle line. Here's a class example 1. We see a couple sets of examples of graphs that are periodic, and it's asked us to find the period and the amplitude for each of the periodic functions. The period is the understanding of one cycle. Sometimes it's easy to spot them. Other times, when we get to much more advanced questions, we'll only be given part of a cycle, and we have to decode that either from the equation or from the information given. In this case, we can choose anywhere we want where we see a repeating pattern. Personally, for me, this is where I see it. 0 and 8. What do I see? I see this pattern repeat between 0 and 8. We would call the period 8. I don't know what unit it is. Could be seconds, could be days, could be months. Who knows? Could be mood swings for every class. I have no idea. There's the period. The amplitude is defined as to how far away it goes up or down from the middle. It's fairly obvious if I look closely here. Zoom, zoom. Hope that doesn't crash. I think I just crashed it. Nope. Good. The amplitude is defined as to how tall it is. Here it goes from, this is the vertical looking. So we're looking at two different things this time. One horizontal, one vertical. And it's just from the midline. Here it's from 0 to 10. We would say the amplitude, amplitude, is 10. We have answered the analysis of this basic graph for this one. Let's move along here. To B. Yes, to B. Okay, like I said, some questions are not as easy to spot per se a pattern. One of the nice things that you can look at are these things called nodes. You don't have to officially know those for math, but nodes are come in handy. Namely, peaks. There is a node, and there is a node. I can look at these ones and say, that's when I see a repeating pattern from crest to crest in a physics wave. It appears that I'm at 3 to 9. How much difference in the domain is from 3 to 9? Well, that means the period looks to be about 6. The amplitude for this one is a little trickier because I told you that you had to get from the midline, and now the midline is not here. The middle of this graph, as it calls oscillating, is not on the axis this time, or whatever axis that would be. You can find it two ways. One is to do a visual inspection and look to see where the middle is. You might try, and you may or may not succeed by saying, oh, there's the middle line. Not the best. Or, here. Not the best. But as opposed to guessing and testing, you have an idea of what we have, an average. We're going to figure out the average. Because if we can figure out the distance between these two guys, we can figure out halfway between them. So if I take 6 plus minus negative 2, my apologies, minus, to figure out the absolute distance, back to my pen tool, minus negative 2, I get a distance of 8. Slash that in half. I get 4. Wait a minute. That's the distance between the midline. Remember how I said 4 wasn't this middle? That's right, 4 is not the middle. I know this might be tedious, but 4 is any distance away from a maximum or a minimum. So if I just count 4 units away, up or down from a maximum, so 6 going down 4, it appears that the middle would be 2. If you want the midline, that comes in handy sometimes. The amplitude shall be defined as from the midline to the maximum or minimum. So we'd say for this question, the amplitude is 4. Moving along. Hope I don't crash my little video display. Oh, there's a third one. Yep. Okay. This is if you ever played with an oscilloscope, an actual one. Certain ones don't give you that nice wavy feature. Some of them actually have a step feature like this. But we can still figure out the amplitude and the period from this one. So again, for a period, ooh, that's bad. Red, scary. For a period, we're looking again for a repeated pattern. It's weird because you could look at it this. I could see this way because it has to come back to its starting point, or you could have seen this way, back to the starting point. It doesn't matter where you count, long as it's returning to the exact same spot. So I'm just going to pick on this one here. In fact, a totally different one where I'm going to go and starting from a spot, go up, over, down, across, back to another spot where I have to go up, back, over, across. So the pattern, if it doesn't crash out on me, is this one. Here's a pattern as well. The period is the domain in which it repeats. From 15 to 25, this one, the period is 10. I'm going to use that same technique for the amplitude business. I'm going to see if I can find the middle line. And this time, I'm going to use the numbers 6 and 2. I'm trying to find the average between them. 6 minus 2 is 4. Divide that in 2, I get my amplitude. Which it's kind of obvious that the middle of the graph is from 6 to 4, or an amplitude of 2. One thing that comes in really handy about this, if I can do it right, probably not perfectly, the amplitude can be seen from the middle line up to the maximums. Again, there's not a maximum visibly there, but that is what the amplitude is. The amplitude is from the midline up to a maximum point. So there is an amplitude value right from there. So our first task, we're going to be graphing the basic primary trigonometric functions. We are going to need all of our brain power to see what's going to go on with this one. My mouse is off there. I need to see what I'm doing. We're going to graph the sine of x, the cosine of x, and I believe in the homework, the tangent of x. So I will be modeling the sine of x for you. You will be investigating the cosine on your own, and then subsequently, for your homework, the tangent of x. What we're going to be doing is we're going to analyze it first and foremost from the basic domain of 0 to 360. That would be, oops, that's a bad color. It's glitching out on me here. That would be a single rotation of the values of sine or cosine or tangent as they go around one circle. All right. Okay, we're going to use the graphing calculator, and we're going to develop the sine of x as a class lesson, and it says the cosine and tan will be in the assignments. Next page. Okay, so we're going to be graphing the sine of x in degrees. I'm going to pull this over here. Hopefully you can still see that on a big screen, or not. I will zoom in at some point for those who are farther away from the board. I'm going to have to bring in the handy-dandy TI calculator. I'm going to use this one because I can make it full screen if I need to. First things first, check the domain style. That would be degrees. That also means our mode of our calculator also has to be in degrees. So I've got my calculator on. I don't know if you do yet. I'll pause thinking and hope that you'll get your calculator out. Mode. My last time I was in my calculator, it was in degrees, so I'm good to go. You are probably not. But make sure you're in degrees. Get out of here. Alrighty. So, Trig, these TI calculators have a built-in feature. Let me just go full screen. It's going to be scary. Full screen. Alrighty. The TI calculator has a built-in window feature for trigonometry. In fact, if you press the zoom, I think it's F3. Yep, there it is. F3, zoom. Scroll down to 7. You have a trig graph. There's nothing on there because you haven't plotted anything. I'm going to make sure I'm in the right mode. I just press zoom trig. Again, F3, 7, zoom trig. That is kind of what the graph is supposed to look like, blank on a Cartesian plane of degree mode. What's our domain? Let's match it up here. It looks like ours goes between negative, I pressed the window button by the way, negative 352. I'm going to need to go to negative 360 to hit that number by the way. So I'm going to change that to 360 and to 360. One thing I didn't really pay attention to was how much every step is. It assumes you want to go by 90s. That's just fine. Okay. The Y minimum says -4. Let me just take a quick peek again as to this one actually only goes up to 1 and a little bit, so I'm going to change that scale. Full screen here, full screen view. I'm going to change the scale so I'm just bigger than 1. So again, -1.2, I don't know, doesn't really matter, and then 1.2. And maybe every 0.2, I don't know. If we hit graph again, the graph is now up here. It's going to be 1, and this is going to be positive 360 to the far right, and negative 360 to the far left. Each one of these represents 90 degrees. That's actually more important as a scale, pardon me, to use for this setup. Now for the fun. You go to y equals, and don't graph 56. We're going to type in the sine of x. I need to see with the button because I forget where it is. Sine of x. You should close the bracket for good practice measure. All right, emulation, back to full screen. And lo and behold, for the first time in all its glory, the sine function. F5. There it is. Ooh, pretty. I'm going to take a screenshot of this because I can. Full screen, true colors, clipboard. Yes, just the LCD. Alrighty, back. We're going to get rid of this guy because I don't need that anymore. Okay, I'm going to take this over here, go Control V, pop that little screenshot there, move it over, and there's the information that I need to remember. Okay. So it says you're supposed to use a table of values. Where's the table of values? Well, if you want to know, you can just go ahead and go to second graph, the table. Now, I don't know where yours was, but mine was set to go up every single degree. That's a bit of a problem. I notice here the scale of the x values are not every 90, but every 90 subdivided by 3. That makes it every 30. For convenience sake, let me just go to big screen here. Emulation full screen because I can't even see that. I don't want to actually plot every single degree. I actually want to go up by 30s. So how do we do that? We press second table. Second window. This is the table setup. For this particular case, it says start at 0. Sure, why not? If you press the down arrow key, this is the delta table. This says go up by whatever you specify. By default, it's always by 1. Please note that we're going to have to change this back to 1 when we get out of all this stuff, when we're done graphing this stuff. We're going to want to change that to 30. So now, if I go to my second graph, I can see all the values of 0, 30, 60, 90, 120, 150, 180. And I can just press the up arrow key and go all the way to negative 360. So, it's now time for you to record these values and put them in the table on the document. I'm going to get out of the screen. Namely, you're supposed to put the numbers, let me just specify that here. You, and your job right now, is to translate what I just did all onto these table values here. It says to plot the points below. I am going to let you, oh, actually, I was actually right on the 1.2. I wasn't even paying attention to that. That's called serendipity. All right. So I will let you do that, and your teacher or whoever's supervising you can press pause right now and wait for you to fill out those table values, and then come back when we're ready to plot. So I hope you're ready back to plot. Now, this is important about plotting the points. I'm going to do it in a very particular fashion because this is a very important starting point where you should technically start a natural rotation. Now, it says to plot the points. Where you should start is 0, right here, at 0. I know for a fact the graph, although you can fill it in as it goes, I'm just going to do these very special intervals of 90 degrees. This is what's really important right here. 90 degrees, the graph is at 1, or rather the sine value is at 1, because we know that the y value is the same as the radius at 90 degrees. And then as it flows around, the rotation as it goes to 180, the sine value, the y value, is nothing. And then as it goes down, oops, that was way too far. As the rotation of the angle goes down to that special case of 270, I went back, 0. At 270 on the rotation, the graph has a y value the exact same as the radius at negative 1. And then full discord all the way back up to 360, the y value, how much height there is in fact back to 0. There are particular values where it's 0.5. The sine of, I believe it's 30, happens to be, 60. 30 is the 0.5. There we go. And then it goes 0.5 symmetrically, and then negative 0.5 is about here, right? And then over here, that's about that. Please note how I'm able to do this. My number one thing I'm trying to do is establish this shape. All I actually need are the 0, the 180, the 90, the 180, and 360, and this is the actual sine wave itself. This is where you start. This is the sine wave. Okay? You can then fill out the values as they go. It says you're not supposed to connect the dots. You should connect the dots, because I've already explored, or rather revealed, what it's going to be as you connect all the dots. Negative 180, 270 is the reverse up there, and I'm just going to go curves up, and whoops, my mouse moved, or my pen moved. And of course, at 450, it's back up here. It's 90 degrees more, and then back down to 540. Super important, that middle stuff. Okay, all this stuff is the important shape you're supposed to recognize as a sine wave. Okay, now it's important to note it starts in the middle, and as it makes a full cycle, there it is, a full cycle, 0 to 360. There's the period it makes, goes from the middle point to the middle point. That's the big idea of a sine wave. Now it says to continuously graph all the points, and it's periodic indefinitely left and right. Well, how do we know it goes indefinitely left and right? Well, that's what our good friend Desmos will tell us. Back here with Desmos and sin x. Now, of course, these are in radian modes, by the way, just in case you didn't know that. Whoops, I don't want to switch over yet. I didn't want to do that. Okay, bring that down. All right. These are in radian measures by default on Desmos, by the way. You can also do it in your phone. Switch over to degrees. Oh my goodness, it's like super flat. Why is that? Because my domain is not between 0 and 360. And there it is. There's the 360 wave. And if I want to stretch this out to make it look pretty, there it is, the 1. And of course, when you scale it in, whoa, it goes on forever, indefinitely left and right. So Desmos, by the way, always wants to default back to radian on your phone if you're ever doing it. Same, your calculator also likes to graph it in radian measure as well. All right, so there's a sine wave. Again, you'd start at 0, go up to 1, at 90. Again, it's just, these are on a different scale altogether. If I change my scale, that's what I can do. X-axis, what my step is, if I said 90, now it looks pretty. Every 90 goes up to the top, back to 180, back to the middle, 270, down to the bottom, 360, there it is. I can even specify between 0 is less than, X is less than 360. There is a full sine wave. Of course, the unlimited, restricted domain, forever. The same thing goes on. Okay, that's that point there. Back to the boring old workbook. Hope the graphic card can handle that. All right, so now we have the idea of the sine x function. We have a visual of it. Okay, and it says, let's start doing some analysis. Oh boy. It's hard to have that analysis when you don't see the graph in front of you. So what I'm going to do is I'm going to grab a screenshot of Desmos. Okay, I am back with my Desmos screenshot, and I'm only going to look at between 0 and 360 for right now. The domain, by the way, is looking left and right. I guess I should get off red. Left and right, what values of x can go into sine? Those are degrees. Well, what angles can you have? Guess what? It could be anything. I'm going to go over to B, as in up and down. It seems like there's a limitation. In fact, there is. Looking up and down, I can see a maximum and a minimum, which I have to account for. This graph oscillates between the lowest value of -1, y, and 1. So it's less than, but it could be equal to 1 or -1. So the range oscillates between -1 and +1. And then, of course, it's continuous, so I can put YER afterwards. It's up and down forever throughout that. I'm just going to erase this part of it, yoink, because I can. Amplitude. Well, the nice thing about this one is I can see it. Again, amplitude is the distance between the midline and the highest point, or the lowest point if necessary. This scale is a little deceiving, but it is, in fact, 1. So the amplitude is just simply the quantity of 1. Erase all that. Period. Again, looking left and right, can we see when this graph repeats itself? I'm going to start here for a very particular point that the graph appears to have a pattern of this. This is the sine wave, and the idea of period is from when does it go from here back to here? Naturally, it's a 360 degree period, because that is the rotation of the angle when you're moving around on a terminal arm when it returns to its spot. That's why it's 360 on the degree mode. I'm just going to erase this little wave, and going over to the x-intercepts. Notice how it's plural. I'm going to zoom in on this one because I can. The x-intercepts. There's our Desmos screenshot. It's not the live, beautiful version. Now, here's the funny thing about this one is that there is an x-intercept because it crosses the x-axis. And looking across, there's another one. And looking across, and lo and behold, there's yet another one. And if we know this thing keeps going on forever, guess what? There's a heck of a lot more x-intercepts. In fact, there are infinitely many x-intercepts as this domain goes on forever, so there will be an infinitely many amount of x-intercepts. So as we approach what's called the standard of excellence about developing a formula that accounts for all of them, naturally, if you can determine the fact you have the x-intercepts at 0, 180, 360, that's at least a minimum start. But if you recognize how often they repeat from each other, little smiley face there, you can then start figuring a formulaic pattern. Well, if you start the x-intercepts at angle of 0 degrees, and it happens to be every 180, you seem to get another x-intercept. So the answer for the x-intercepts will be the angle of 0 degrees plus 180. Now you're going to use n, and n-e-i. Because not only does it go to the right, it also happens, although it's cut off here, but I'm smart enough to think about this, it also shows up. Oh yeah, I can write on this one. I totally forgot. I love this feature. It also, I can write on Desmos. That's so amazing. It also goes to the left every 180. Look at that. I know it's pretty small to see on the big screen, but every 180. That's why I have the NEI, because, or sorry, N rather, 180N, quantities of 180, and NEI, because it's not only times positive 1 or positive 2, it's times negative 1. There's a negative 1N. There's a negative 2N's. That makes 360. Negative 3N's. That makes the 540. Okay? That's why we use the little formulaic idea. There's more than one answer. In fact, there's a formula for all the answers. That's where we get the idea of a general formula again. When we are solving answers for equations, that's why that comes into play, understood. I'd also like to take a point to note here about the starting point. Right here, this x-intercept happens to be what we call the starting point of the graph. Normally, we start at 0, and it happens to just go up. The natural pattern for a sine wave is to start at 0, 0, and go up to the right. That's important when we start doing transformations. Remember those hinging points from all other functions of logarithms and exponentials, vertex and quadratics? Well, this starting point is a really key thing that we need to pay attention to. Natural graphs start at 0, 0, and then head up to the right. I'll keep that in your back pocket mentally for later. The y-intercept happens just to be where does the graph cross the y-axis. And there is only one y-intercept. And it happens to be zilch, 0, nothing. Namely, it's at 0. Not there is none, but there is a 0 value. Y equals 0 value. Probably don't need to y equals because that would be that could be confusing as to an asymptote. Okay, let's move out of here. I think that's practically all the examples except this one. You are supposed to try doing it for a radian measure. Okay? You're supposed to sketch the graph. Sorry, it's way zoomed out on the next page. The student was asked to reproduce the graph in radian mode. Watch this. Can I erase this board? Oh no, that's going to take a while. Can I not erase all this? Oh goodness me. Oh, I think I have erase, right? Click. Erase. Yes, awesome. Okay, so like I said, Desmos, just to reveal things because it says we're in degree mode, radians. Oh my goodness. what's just happened there? I just changed to radians, and it's just like, oh man, it just filled in thousands and thousands of sine waves. But if you just go back to the home button, it naturally does what you're supposed to do. The question is, what should be the window on a TI calculator? Again, if you notice the fact, I'm going to see if I can get this marker just a little bit thicker here. That should be better. It's a little bit better. There's the sine wave itself. There it is, the up and down motion there. And see, Desmos is so smart, it's telling you what kind of window you should have, namely the x-intercept. Look at those numbers, 0, 1.8, 3.6, 5.4. I wonder if anyone can anticipate what quantity that is, namely, what's the matchup for 360 in radian measure? Big reveal. The approximated value of 2 pi, which is about 6.28. If I switch back over my mouse, see, Desmos is really smart. Whoops, mouse. Not hard to see the label though. I don't know if you can see that, but there it is. Desmos is so smart, it knows to give you radian measure precisely. That's why you're not allowed to use Desmos on any tests, etc., because it gives you exact answers, which conceptually you need to know. That's why you're not allowed Desmos. But great for learning, figuring stuff out. Okay, back to this particular desktop. I've shown you what a sketch looks like. You are now assigned the task of drawing and looking and exploring the cosine. Will Mr. Weedman allow you to use Desmos for figuring out what a cosine graph looks like? And for the sine graph in radians? Sure, why not? Not a problem. You're learning something new for the first time. That is, you have your homework scheduled for the entire course. If you can please complete your homework, I will go up and take up any questions afterwards before tomorrow, or the next day rather, where we discuss changing the transformations, and the first one to begin with would be amplitude. Thank you, and have a great day.